Okay, at last we can talk about self-organizing map algorithm. So this algorithm takes data and the dimension of the grid as input. So by the grid dimension, I mean height and the width of the grid. So for example, here in this line, we create the grid with width equals to 5, height equals to 5. So it makes 25, 5 times 5, it makes 25 neurons. So 25 neuron is initialized. What does it mean? They have coordinates in the two grid and their weights are initialized randomly. Remember, there is a mapping from grid space to data space. The weight, dimension of the weight is same as the dimension of the data x. Okay, so we select a random data point from the data. We select it, okay. Now, after that, we find the best matching unit and its neighbors. So what is best matching unit? So there is a data and there are neurons in the grid. Okay, from among these neurons, who is the best matching unit? How do we understand? We look at the weights of each neurons and we calculate the distance, Euclidean distance between this data point and the weights of the neurons. Who is the closest one? For example, this one, now it is the best matching unit. So it is closest in terms of its weights to the selected data point. So we have best matching units now. Okay, now the learning phase begins. So what is learning? So this, for example, this neuron is selected as a best matching unit. So what will happen? So its weights will become closer to this data point. So think about it. So this data point, actually, it just pulls this itself, but not only this one comes, its neighbors also comes with itself, with this best matching unit. So this is what happens in reality. So what is the update rule here? Next weight equals to previous weight plus learning rate times neighborhood function times data points minus weight. For the moment, don't think about this part. Just think that these two, learning rate and neighbor function, returns 1. So in this case, what is the result? Weight equals to weight plus data point minus weight. So weight equals data point. So data actually, in this case, if there is learning rate is 1 and neighborhood function returns 1, so and this is the best matching, this is the data point, then this will become equal to the data point. The weight of this neuron will become to the data point. Okay, so at the end, but learning rate and neighborhood function is not 0, is not 1. So the new value of the weight will be a combination of, linear combination of this data point and the previous weight. So it becomes closer and its neighbors also becomes closer. I will show how its neighbors are affected in the coming lectures. So here, in the coming slides, I mean. So here we find the best matching unit. Best matching unit becomes closer to the data point and its the neighbor neurons also becomes closer to the data point. If a similar data comes, then these two data, they are similar data, and maybe they are clusters. They are data from the same cluster. Then this best matching unit will become much more closer to this data. Again, I repeat, what is best matching unit? So neurons, you can think them as agents that are competing with each other. They all want to be the best matching unit. In terms of weights, there is a winning one, and the winning one goes or becomes closer to the data in terms of its weights, and its neighbors also becomes much more closer to the data. So if there are clusters of data and the neurons that are closer to the grid will be mapped to the same clusters, and we will see it. Okay, this is an iterative algorithm. In this iterative algorithm, learning rate is decreased in each iteration, and
hold on, Frank, I will show.
And radius of the neighborhood function also decreases. I will continue from here. For the moment, let's finish.